Welcome to the debate. Today we're tackling really one of the biggest cracks in the foundation of modern physics. The fact that general relativity, quantum field theory, and, well, the sheer reality of thermodynamics just don't talk to each other. We've got these incredibly successful descriptions, gravity as geometry, the quantum world, the arrow of time, but they seem fundamentally separate.
Right, it's this fragmentation that's the real headache. Each theory works beautifully in its own domain, spectacularly so, but try to put them together and the seams show badly. The big question is, can we find a single, maybe simpler source law underneath it all? Or do we just have to live with these separate pillars?
And that sets up our debate perfectly. Is the universe ultimately governed by a single, inherently dissipative law, what's called the time force hypothesis, or TFH, where irreversibility itself is the engine driving everything, or do the established frameworks GR and QFT, which are fundamentally time-symmetric, remain the bedrock, with dissipation just being something that emerges later? I'm arguing for TFH, suggesting it offers a remarkably cohesive picture with just one key parameter, alpha 0.
And I'll be defending the status quo, arguing that GR and QFT, built on deep symmetries like time symmetry, are just too powerful and well-tested to simply discard. TFH, from my perspective, proposes a really radical shift in our understanding of reality, one that's frankly unverified and perhaps solves a problem we can manage within the existing structure, even with its gaps.
Well, the real draw of TFH, I think, is its austerity. It starts with the very simple idea. The universe is fundamentally described by a single scalar field, let's call it phi, and this field follows one basic rule. Its waves are always slightly damped. There's a tiny bit of friction inherent in everything. So irreversibility, this damping rate alpha being greater than 0, isn't an afterthought, it is the fundamental law. Everything else, time, space, matter, these are just patterns that emerge as this field constantly redistributes its energy, always seeking equilibrium. It's called the equilibrium principle.
Okay, but the immediate cost, as I see it, is throwing out fundamental time symmetry. I mean, GR and QFT derive so much power from being time reversible at the most basic level. Their laws work the same forwards and backwards in time. You're taking dissipation, which defines the arrow of time, and putting it right at the core as the source law itself. Where we see the reversible case alpha going to 0 as the fundamental limit, you're making the dissipative term the anchor. That's a huge conceptual leap.
I understand that reaction, but look at what you gain. This single constant, this universal damping rate alpha 0, it does an incredible amount of work. We propose identifying it directly with the present-day Hubble expansion rate, h0. Think about that. One number, alpha 0, connects the absolute lowest level of decoherence we might see in a lab experiment, quantum friction essentially, with the large-scale acceleration of the entire cosmos. That's 30 orders of magnitude linked by the same physical constant. Cosmic expansion and quantum fuzziness become two faces of the same dissipative coin.
But it comes at a significant price, conceptually. You're saying space and time themselves aren't fundamental stages, but just relational descriptors derived from how this phi field changes its gradients. Gravity isn't space-time curvature in the GR sense anymore. It's more like a flow effect within this field. That completely rewrites our century-old understanding of geometry.
But consider the elegance it brings to explaining fundamental constants. Take c, the speed of light, or h bar, Planck's constant. In TFH, they aren't just numbers you plug in. They emerge. Quantization itself isn't some separate ad hoc rule. It arises because in a constantly dissipating system, any stable repeating pattern like an oscillation has to find a balance. It needs to manage its internal energy flow against the constant background loss rate, alpha 0.
Right, so you're proposing H isn't truly fundamental, but it's this emergent quantity, this HF, which is basically the field's energy flux, epsilon phi, divided by the damping rate alpha naught? Is that the idea?
Precisely. It's the action quantum needed for a state to persist to hold itself together against the universal flow. It suggests H is a consequence of living in a dynamic, dissipative universe, not an arbitrary input constant.
I'm sorry, but I'm not quite convinced this makes things simpler overall. To get actual stable particles, things with mass, spin, charge, the stuff of the standard model, emerging as, topological knots or structures in this phi field, you need to add complexity back in, right? You need a nonlinear term, something like plus beta phi 2 phi, to provide self-interaction, to stop the structures from just dissolving away. That feels like you're reintroducing the kind of complexity found in other field theories. And claiming this beta is somehow fixed by the flow needs, rigorous proof beyond just dimensional arguments, especially when it comes to reproducing the whole particle zoo.
Aha. But look at the quantitative results it can point to. This emergent action scale gives a natural explanation for the mass scale of strong interactions, the Young-Mills mass gap, a notoriously difficult non-perturbative problem in standard QFT. TFH suggests this mass gap, around 1.6 GeV, is set by this very flow invariant. Why? Because the same cosmic damping alpha naught acts as an infrared cutoff for the gauge interactions through this dissipative equilibrium. That's genuine multiscale consistency, potentially without arbitrary tuning.
That is interesting, I admit, but the standard QFT framework does recover perfectly conservative reversible physics in the limit where dissipation vanishes. You have a high bar to clear to show that giving up that fundamental symmetry is justified by the, let's say, effective parameters like epsilon phi and beta you need to introduce. The burden of proof is definitely still on TFH here.
Okay, let's shift the cosmology then. This is where TFH really shines, I think, offering a unified picture for the dark sectors, dark energy, and dark matter, stemming purely from the dynamics of phi. Take dark energy. It's not some mysterious vacuum energy, lambda. It's simply the effect of the field's kinetic energy dissipating away globally, everywhere, all the time. Because the underlying damping rate is alpha 0, the cosmic expansion rate naturally gets driven towards H0, which looks exactly like an equation of state, W lambda approximately -1. Cosmic acceleration is just the universe settling down, macroscopically manifesting the fundamental dissipation.
Now, this is where the hypothesis becomes extremely testable, but also potentially quite vulnerable. Your claim about dark matter is even bolder. It's not a particle at all, but an effect of how the field responds differently in different regions. Field warping due to spatial gradients in its susceptibility. This leads to a very sharp, falsifiable prediction. In the outskirts of galactic halos, the density profile must fall off precisely as r to the -3. No adjustable parameters. That's incredibly specific. If detailed observations find significant deviations from a pure r to the -3 tail, or if it doesn't hold universally, then that whole dark matter explanation is in serious trouble.
I agree completely. The predictions are sharp. And perhaps the sharpest, most decisive test involves gravitational waves. Because TFH posits universal dissipation affects everything. It predicts that space-time itself, the metric, must feel this damping, proportional to alpha 0 divided by the wave frequency omega. This means gravitational waves' amplitude should actually decrease slightly as they travel, with the attenuation per wavelength scaling like 1 over frequency, delta H proportional to f-1.
That's the killer signature. It would be incredibly tiny, maybe 10 to the 21st per cycle for typical sources. But it's absolutely unique to this dissipative idea. We'd need the next generation detectors, Cosmic Explorer, Einstein Telescope, to even have a hope of seeing it. But if those instruments run for, say, 5 years and find no sign of this frequency-dependent damping, well, that would be extremely strong evidence against the core idea. It would strongly suggest the fundamental laws are conservative, not dissipative.
And that's exactly the kind of empirical test a new fundamental theory needs. If alpha 0 doesn't show up in the gravitational wave spectrum in that specific way, then TFH, at least in this form, is falsified.
Okay, but let's loop back to fundamental consistency, because this is non-negotiable for the status quo. Physics relies on energy momentum conservation. Dow below mu, T mu nu equals 0. If your main field equation for phi has an explicit damping term, an energy sink, how do you maintain global conservation? Where does that energy actually go?
That's a crucial question. And you're right, if you only look at the phi field dynamics, the part generating matter and gravity, it looks like energy is being lost. But that's because it's an open subsystem. The full consistency comes from what we call the alpha unitary completion. Imagine a simpler analogy, a cup of hot coffee cooling in a room. The coffee loses energy, sure, but the total energy of the coffee plus the room remains constant.
So you're essentially postulating an unseen room, an effective bath variable, let's call it psi, that absorbs the energy phi loses. Doesn't that just shift the complexity into defining this total phi plus psi system that is conserved?
It's structured complexity, though, arising directly from the single dissipative postulate. The stress energy tensor for the total system remains perfectly divergenceless. The evolution is completely positive and trace-preserving, satisfying all the requirements of quantum consistency. The apparent energy sink in the phi equation just correctly describes the energy flowing from the observable subsystem into this unobserved equilibrium background. It's not violating conservation. It's accounting for energy flow within a dynamic equilibrium. We're seeing balance through flux, not through static symmetry.
Look, ultimately, the status quo frameworks, GR and QFT, remain incredibly precise and conceptually grounded within their domains. TFH offers this grand unifying narrative built on irreversibility, which is compelling, I admit. But its key predictions, the specific GW damping signature, that exact R-3 halo tail, potential redshift drift effects are very sharp, very specific, and crucially, not yet confirmed. The reliance on effective field descriptions in this alpha ununitarity suggests there's still significant complexity, even if the starting point seems minimal.
But the strength, I maintain, is that multi-scale consistency. One constant, alpha 0 equals h0, potentially explaining the arrow of time, quantum action, cosmic acceleration, and the dark sectors across, again, 30 orders of magnitude. It reframes physics away from static geometry and time symmetry towards dynamics, flow, and inherent time asymmetry. If the next generation of precision cosmology and GW astronomy finds that same constant, alpha 0, showing up consistently, linking quantum decoherence to cosmic expansion, well, then this flow perspective might just be how reality actually works.
It really comes down to the observations, doesn't it? Which picture aligns best with the most precise data we can get? Does the universe fundamentally respect time symmetry at its deepest level? Or is that symmetry just an effective description of a reality that is at its core always flowing, always dissipating?
Exactly. It's a pivotal moment for foundational physics, I think. In exploring both possibilities, the established symmetric view and this alternative dissipative one is absolutely essential if we want to push our understanding forward.